Let's get started. Hi, everybody. Welcome to another round of IRIS-HEP Fellows Talks. Um, we have five talks today. First up is Jelizaveta. You want to go ahead and share your screen?
Okay, so hello, my name is Jelizaveta, and my project topic is improving latency and scalability of the user runtime job log collecting and exposure in REANA. And my mentor is Dr. Tibor Shimko. REANA is a reproducible analysis platform which was created for the purpose of reusing and reinterpreting research data analysis. The researcher writes his data analysis workflow and submits it to REANA cluster. REANA cluster schedules the workflow execution on a computing backend, which can be either Kubernetes, Slum, or htconda. It also monitors it, persists the results, displays them to the user via REANA client CLI tool or web browser. Data analysis workflows are defined in YAML files, where it is possible to specify the type of the workflow engine, one or multiple steps, which can run sequentially or in parallel. On the top right, you can see directed cyclic graph of a workflow, which has both sequential and parallel steps. It is also possible to specify a Docker image, the command to execute, additional files, custom parameters, resource limits, and so on. After the workflow submission, the researcher can go to REANA Web UI and inspect workflow execution progress, or alternatively use REANA Client CLI tool. Workflow and job status is reported in real time, but workflow and job logs can only be inspected after execution completion. So on the right, you can see a screenshot of an example message, which is currently displayed to the user while the workflow is still running, and says that the workflow engine logs will be available after the workflow run finishes. And at the bottom, there is another screenshot that shows the logs that are displayed after the execution is completed. This works well for short-running jobs, but some jobs can run for hours or even days, and the user has no feedback of whether his code is executing correctly. So the goal of my project is to enhance REANA workflow and job logging system with the possibility to capture logs of executing processes live, which means while the workflow or job is still running. And there are three common alternatives for log collection in Kubernetes: daemon set, sidecar, and Kubernetes API. This will be explained later. And additionally, there are multiple log storage options and login agent options if used. And then alternatives can be improved further by adding log result caching and by optimizing REANA REST API, as it currently retrieves logs for workflow and all its jobs at the same time. But it could be redesigned to retrieve only one job log at a time. So I've created prototypes for various alternatives with different storages and different login agents for evaluation. And the code can be found in GitHub repositories, which links are provided at the bottom of the slides. And the first alternative is daemon set. A daemon set is a set of pods where at least one pod runs on each Kubernetes node. So on the right, you can see a diagram that displays two Kubernetes nodes. On each node, there are pods whose logs are stored in files on node's file system. On each node, there is a pod of a login agent, in this case, Flanbit. It has access to these log files and reads them and pushes the data to some storage. And this is the most common technique used for logs collection in Kubernetes. The next alternative is a sidecar. A sidecar is a container in a pod that runs alongside some other container and shares network and file system resources with it. On the right, you can see a diagram of a pod with two containers. One of them is a Python process which logs to a file, and login agent reads this file from another container and pushes data to log storage. The last alternative is to retrieve logs from Kubernetes API. Kubernetes API is an important component of Kubernetes cluster. It exposes REST HTTP API. It is possible to collect pod logs by making a request to logs endpoint. It is also true for all alternatives that the logs for a pod are available only while the pod is still running. So in this third alternative case, there should be a service implemented that retrieves the logs from the API and pushes them to log storage. And this solution risks impacting whole cluster in case the load on Kubernetes API gets too big. There are also multiple log storage alternatives. We have evaluated three options: PostgreSQL, Elasticsearch, and OpenSearch. PostgreSQL is a current REANA database, so in case we use it, no new tools need to be introduced. Elasticsearch is the most popular choice for log storage, and OpenSearch is its open source alternative, and it is recommended for use at CERN due to its open source licensing. After prototyping, we decided to go with OpenSearch for daemon set and sidecar alternatives and use PostgreSQL for Kubernetes API option. There are also multiple logging agent alternatives, which are only suitable for daemon set and sidecar options. Fluentd is currently used at CERN to collect logs for Kubernetes clusters, but there are plans to deprecate it in favor of FluentBit, which is very similar but much more resource efficient. Logstash is commonly used together with Elasticsearch and belongs to the so-called Elastic ecosystem. Vector is another popular choice, but it has quite complex configuration and incomplete documentation. So after prototyping, FluentBit was selected for further tests. So after prototyping the alternatives and selecting the configurations which seem the most acceptable, I've performed HTTP benchmark for REANA logs retrieval. And we have created a REANA test Kubernetes cluster with 43 nodes and run benchmarks with 3,000 parallel jobs, each job emitting 1,000 line of logs. So I've submitted 60 workflows to REANA test cluster, waited until all jobs are running, and did benchmarks for 60 seconds each. So for 1, 2, 5, and 10 requests per second to REANA HTTP API endpoints. And here are the results for 1 and 2 requests per second. So first 3 rows are plain alternatives deployed without caching or API optimization. And you can see that the fastest plain alternative is sidecar, and the slowest one is Kubernetes API. So next 3 rows are for cached alternatives. You can see there that mean and P50 improves a lot, but P95 stays nearly the same as well, caching expires sooner or later, and some requests have the same times as in plain setups. And the last 3 rows are cached and optimized alternatives. And you can see that response times are much shorter. And these are the results for 5 and 10 requests per second. You can see that with 10 requests per second, all plain alternatives start to time out at some point. And with caching and optimization on the bottom, all setups seem to perform nearly equally well. So after benchmarks, I also performed reliability tests. and basically created some scenarios for each setup, like pod eviction, pod deletion, code exceptions, out-of-memory errors, node crashes, node storage pressure, and then noted whether there are entries in logs that notify the user of this specific event. So on the right, you can see first example of triggering pod eviction using kubectl evict pod plugin. On the right, you can see first the example of triggering pod eviction using. Oh, I'm sorry. Below it, no, 1 minute. So below it, there are screenshots of logs with eviction and out-of-memory warnings. And here are the results for reliability tests. Daemon set seems to be the most reliable and does not display any error message. Only one case, like with workflow node crash. Sidecar is the least reliable and does not display any errors in 3 scenarios. And Kubernetes API setup also has only one case when the error is not present in logs. But in this case, all job logs are lost altogether, as workflow pod does not have opportunity to collect them and push to permanent storage. So eventually we decided to go with daemon set, Fluentbit, and OpenSearch option. To implement it, I have made changes to REANA Helm chart, Yana cluster components, REANA clients, and documentation. So OpenSearch configuration is production ready with TLS, authentication, authorization, and multiple storage options. Code is extensively covered with tests and adheres to best practices. Here are the screenshots of live logging functionality. After the changes, you can see that the workflow and job status is running. The logs are displayed to the user. And at the bottom, there is REANA client logs command change, where I've added a follow flag. It behaves similarly to tail -f command. So it retrieves logs and updates the output for the user so he can monitor his data analysis workflow execution. So thank you, and do you have any questions?
Thank you. Nice talk. Alex?
Hi, very interesting project, and nice to see all the results and the measurements that you have here. In your benchmarking results, the times that you're showing, just to make sure I understand correctly, this is the time effectively to request and get back the log. So it's sort of the time, not of the work that's actually being done on REANA, but you wanting the log, right?
Yes, log retrieval.
All right, okay. Does the logging have any kind of negative impact also on the job you're actually running in REANA? Is there a downside there, or that's negligible in terms of performance impact?
Negligible. I think I did not notice any slowdowns or too high resource consumptions and so on.
Okay, all right, that sounds good. Thanks.
All right. Any other questions or comments? All right, thank you. Up next is Austėja.
Okay, so my project was called Develop of Clad Tutorials for CMS-HEP, and my mentor was David Lange. So to understand my project better, we need to understand what automatic differentiation is. And automatic differentiation is a collection of methods used to compute derivatives of functions programmatically. And it's important to note that it's not numerical, so it calculates the derivatives of functions precisely, well, as precisely as a computer allows it. And it uses the chain rule and the fact that every computer calculation can actually be just divided into smaller elementary arithmetic operations. So there are two main modes of automatic differentiation, forward mode and reverse mode. So let's say we are interested in this function we see here, and we want to calculate a partial derivative in respect to x1. So what would usually happen is the computer would take these input variables, then evaluate intermediate variables that some of them might be used multiple times, and then just use them to calculate the final expression. So what forward mode AutoDiff does is that it takes these intermediate variables and augments them with the partial derivative of that intermediate variable in respect to the, in this case, x1. And so it traverses this tree from left side to right side, and in one pass it calculates not only the function, but also its partial derivative. So this is very cool, but the problem with that is if we want multiple partial derivatives, we have to run forward mode AutoDiff multiple times. So that's where reverse mode AutoDiff comes in. And it's comprised of two runs. So in a single pass, it just collects these intermediate expressions. And in the second pass, it actually computes the partial derivative of the output in respect to these previous intermediate expressions. So it traverses the tree using the chain rule from the right side to the left. And Clad is a plugin for a Clang compiler that enables automatic differentiation for C++. And when provided with a C++ function, Clad automatically generates code that computes the derivatives of that function. So my project's goals were creating a Clad-based demonstration of finding the best fit helix parameters given a set of data points. And well, this is useful. This could be useful because it could be viewed as a simple tracking problem due to the fact that charged particles move in a helical motion when affected by the magnetic field if we neglect other effects. And the other goal was to contribute to Clad code fixing the missing functionalities that we find along the way. And so about the first goal, I will continue talking, but about the second goal, I think I managed to reach this goal because I created a few bug reports, and I also did a small pull request that added some functionalities I was missing to write this. So the plan for the main tutorial was to create a simple function that describes a point on the helix, then create a function that generates points for a helix, but make them a little bit noisy. Then calculate the distance from a helix to a point, and find the best helix parameters with the Levenberg-Marquardt algorithm, and plot the results. So shortly about the algorithm I am using. It combines two optimization methods, gradient descent and Gauss-Newtonian. So gradient descent takes steps in the steepest descent, and Gauss-Newton algorithm just assumes the problem is locally quadratic and finds the minimum of the quadratic. And so the Levenberg-Marquardt algorithm behavior changes based on how close the current coefficients are to its optimal value. This lambda coefficient here is what controls it. And yeah, this allows it to be more reliable and more stable than these other two optimization methods. And in this function, y with a hat here is the distance, the distances from the data points to my helix. And this regular y is comprised of zeros, since that's the expected value. We want the distance to be zeros. And the Jacobians here is calculated taking the y hats and calculating their partial derivatives in respect to the parameters I'm changing. So in my case, I had 6 parameters because that's how I defined my helix. And to calculate the distances to points, I kind of scaled my helix so it could be defined by like this cost, centi, and ht. And if we say that a given point is P and Q is the closest point on the helix, the line segment that connects these 2 points must be perpendicular to the helix's tangent line Q, which gives us this equation, which can be simplified to this equation. And to find the solution, I just performed binary search. And so these are the results of my function. So on here, we can see 2 graphs. This one is actually the one that is produced by my function, because I ran into a problem where it just gets stuck in a local minimum where b is close to 0. So it kind of wants to be a cylinder instead of a helix. But actually, this is fine, because if we know the magnetic field, the parameters a and b, their ratio is known. So just b is the distance between these spirals. So it's the pitch, basically. So if we know the ratio, we can set the b to almost close to 0, and then my function calculates the other parameters quite well. And then we set the b to the actual value as we know it, and we can see that the produced results are quite close, I think. So also, I wanted to implement gradient descent instead of Levenberg-Marquardt, because it is more simple. So it would be perhaps a better way to showcase Clad, but not necessarily a better way to approximate a helix. So I had an implementation, but it got stuck in a local minimum, and the results it produces are very far off from the expected results. So yeah, that's why I didn't use it. And what I learned is that I gained the knowledge about automatic differentiation and Clad, got more comfortable using C++, and refreshed my knowledge about various fitting methods. And I got experience working with a new mentor and with another team. So that's also interesting and very valuable. And well, these are my references. So thank you. Any questions?
Thank you. Nice talk. Any questions or comments for Austėja? No? Oh, thank you. Up next is Lev. Lev, you want to go ahead and share your screen?
So for this first problem, my project was packaging the heap simulation stack on conda-forge. It was done under the mentorship of Dr. Matthew Fakert from the University of Wisconsin-Madison. So the initial objective and the objective of the whole project was attempting to package as many dependencies of the heap simulation stack on conda-forge as possible. conda-forge essentially is a community-driven conda channel where people can download, find, and install packages. In our case, tools. And the dependencies that we were aiming to were LAHAPDF, HEPMC2, HEPMC3, and other packages like FastJet, which was a stretch goal, and PyHEPMC. During the completing of the project itself, our focus was more shifted towards making those tools more cross-platform by adding new platform builds, as well as refreshing conda recipes with newer dependencies. So during this project, changes were introduced to packages like HEPMC2, HEPMC3, and PyHEPMC. So to begin with, for HEPMC2, we're added new build platforms like Arch64, PPC64, and also OSX64. Now these packages are distributed already on conda-forge channels with these same platforms. For HEPMC3, the task was a little bit more trickier because straightforward specifying platforms wasn't that easy, and we actually needed to update some commands and implement a patch, which is essentially just falling back to readlink if macOS is missing a great link. And this took some time, but essentially was finished, and also all necessary platforms were added, and now they're distributed on conda-forge with Arch64, macOS, and PPC64 builds as well. PyHEPMC involved adding all the same platforms, but for now this package is distributed with only Arch64 and PPC64 builds. Through macOS was also added, but for now it is skipped because of some issues that need more deeper investigation in this task. And after completing these packages, a GitHub repo was created where there are some examples of tools that were repackaged. the repo itself uses Pixie package manager to simulate the different environments. This way, it is possible to test how packages are available on different platforms, which I can show you if needed. And this is all. Thank you for your attention.
Okay. Thank you, Lev. Any
Any
questions for
questions?
Lev? Alex?
Hi, yeah, I'm wondering, now you worked on some packages, how similar is the process? So like how much does this translate to now some new unseen package? Is it kind of the same steps, or the issues that you're running into that need to be fixed are very specific per package in practice?
Oh, it's all depends on the package itself, because when you start working on a new package, it can be already outdated, so you need to consider for now re-render the package itself with newly introduced dependencies, and only then you can implement some new, for example, initially we plan to implement Python bindings to, for example, HepMC2 and HepMC3 packages. So when we thought they needed them, but in order to do this, I initially needed to actually re-render them so they were up to date to current dependencies that conda requires itself.
Okay, I see. Thanks.
Thank you.
Any other questions for Lev? No. Thank you, Lev. Yana, you want to go ahead and share your screen and get started?
So, hi everyone, my name is Yana, and I was working, cooperating closely with Petya Vasilova and Sean Mackey, who are working on enabling advanced network and infrastructure alarms project. And I really wanted to thank my mentors. I had been working in a really warm atmosphere with great people, and I'm very grateful to them. And I also was very motivated with like the enthusiasm and curiosity of my mentors. So now let's move on to the project. Last time I was presenting anything to someone else, but my mentors was like 3 months ago. So I guess it will be like a nice thing to provide you with a background or something like that. What is this network we are working with and all this data? So the team, like IRIS-HEP and OSG LHC, they are working with an educational and research network. As we all know, the Large Hadron Collider produces like a huge and enormous amount of the data, and it's very difficult to maintain the performance of the network which deals with this data. So that is kind of a challenge to monitor and to track all the discrepancies and to improve the performance of this network. And if I wanted to present kind of thing that my mentors are working on, I would do that as kind of presenting a product. So the key value or the key product of their work is this alarm and alert system. Here you can see the structure of this system. So if you are a user of the network and you would like to know what is going on in your network and why you have some kind of issues in that, then you can use the web page or like web app there. You can subscribe yourself to kind of issues you are interested in your network, and then you will kind of get the email if this issue occur in the network, and then you also have the possibility to go further and to explore what is the point, what is going on, and maybe you can somehow influence that. So this is how the system looks like. And for example, I was subscribed to networking alarms, and that is kind of my profile and subscriptions there. I can manage them. That is how the email looks like that I got about the issue I was subscribed on. And here you can also see the links to another platform, which is PS Dash. And here you can see in details what is going on, what is this alarm about, and separately all the sites that occurred in that alarm, and get to know better what is going on and whether you can influence it somehow or not. So a little bit more about data which is used for generating those alarms. We can roughly divide it into kind of 3 categories. The alarms are created mainly to detect any issues with trace, throughput, or latency. And maybe I'm not sure whether I should describe that precisely as it's written on the slide. Maybe if you be interested, we can return later here, or you can read it after my presentation. But mainly all these 3 categories are covered with different Python files. There are scripts for alarms are written, and you will know whether, for example, there are some weird outliers for throughput, and some of hosts have this throughput measurements much lower than expected or much higher than expected, and so on. My task was to investigate whether there are new possibilities of creating other alarms for this data. So I started with kind of playing around and visualization of the data to understand what can be done and what is emitted, for example. And here you can see one of my first plots, and with red and orange dots, like the visualization here is the amount of data that is coming to the elastic storage, that all this data from tests are stored. And this orange and red dots showed me that for several hours there were no new records were not coming to the Elasticsearch. So I asked my mentors, what does it mean, and what does it mean, and what can be the reason. And somehow starting from this, we decided that the part which is not covered yet is the infrastructure alarms, the inner pipeline alarms. Because all these tests they are run regularly, but sometimes but we do not know whether all the results are stored in our database, and we can access them later. So that's how the first alarm was kind of created, and this was meta, throughput, latency, trace, and data compliance alarm. So to be honest, it's like 3 separate alarms, because the tests are run with a different schedule. That's why we needed to break out it into 3 separate alarms. And if I want to describe it in general terms, then we are accessing the configurations. Configurations are file the details of the tests which should be run are described. Then we are accessing to them. We are getting all these details, gathering all the hosts which should be found for this set and tests in Elasticsearch. And then we are extracting the data from the Elasticsearch and trying to compare whether what we expected to see there and what we've got aligns with each other. And here on the right, you can see something kind of a JSON file where the structure of the LRM is presented. So it's a kind of a template, and that is what we expect to see in our email when we have such an issue and want to report the user about this issue. And as you can see, I also mentioned here that we kind of had a pitfall here because developing this alarm, I also discovered that some of hosts do not appear in our Elasticsearch data at all. And I also discussed that with my mentors and other people who support all this personal test tools and know better what is going on inside the system. And it appeared that some of the hosts are kind of retired and they do not they are kind of unresolvable. So this kind of made me create another alarm, which is called unresolvable host alarm. On the right, while I will talk what this alarm does, you can see on the right the screen of the email, like what you are getting from this alarm and alerts system if you are subscribed to this exact alarm. So this the problem was that yes, some of hosts can potentially be just simply retired, and we want to know about that because they are mentioned in configurations we are using to sometimes to test other things, and we want them to be up to date. So it reports each host that is retired and notifies the user about that, and also message user about the configuration that this host can be found in order we could go and check whether it's really retired and deleted from configuration. So that is kind of to keep everything in order in our inner pipeline and especially configurations. So this graph shows the results we are getting after like let's assume we deleted all this retired hosts out of our configurations, and we run the test for this meta throughput latency and trace the data compliance. So we'll get the next graph. Here you can see the like kind of issue we are facing. There, for example, we expect that in our PS metadata to be almost 300 of hosts, but the green, blue, turquoise bar depicts the number of hosts we are expecting to see in the Elasticsearch. But the yellow one shows us that we only can see the data for a little bit more than half of this host. And like 3 other pairs of bars are the results for throughput latency and trace correspondingly. So we can see that PS traces kind of gives us the most correct, if I can say so, data. Yeah, and also I started working on the third alarm, but unfortunately I didn't manage to finish it. But we decided that maybe we can include it in, let's say so, kind of presentation manual for the next student, for him to have something to start with, or at least to think about, and like easier immerse himself or herself in the project. So the idea for the next alarm can be this one. Is here on the right. You can see the graph. It depicts the frequency of testing all the hosts for trace tests. And as you can see, the values are like very different. Some of hosts are tested during 2 hours just once or maybe 2 times, while others like thousands of times. And it will be also a good idea to report those hosts that are tested significantly much more than, for example, threshold that can be chosen, and those who are like vice versa tested too few times. But the difficulty here was to choose this thresholds. I assumed, but that was mistakenly, that it won't be difficult to find this threshold, as here we can see the table with all the types of tests, and all these types of tests have schedules, how often they are run. If you can see this 0, that means that the test is continuous. We are running it all the time and getting the data all the time. But other numbers, they are just depicting the schedule in hours. But somehow it appeared not to be that easy to count this thresholds based on the schedule and the type of the test, because some of hosts are sometimes overloaded, and they do not, as I understood, they do not like reply to request as we expect, and so on. And that's why we have like this huge differences. So yeah, that is something that should still be taken into account, and it still needs to be done. So something for next student to work on. Yeah, so I tried to kind of present you this aligns. And if you have any other questions, I will be glad to answer them.
Thank you, Yana. Any questions for Yana? Gordon?
Yeah, that's a great talk. Thank you very much. You may have been talking about this right at the end there. You were adding a bunch of alarms, and like particularly the is it still alive? Is it resolvable? Does it respond to a ping alarm? I would imagine that goes off a lot, just because, as you pointed out, sometimes hosts don't respond to those. Sometimes internet is busy, so those things are low priority, so a router will drop them, etc. How do you filter that so that the person using all of this can decide when an action has to be taken, and when it's okay, it didn't ping today. Oh, it's not pinged for a week. Maybe I need to do something, right? I mean, how is that done?
So all the alarms have their own schedules, and for example, the one you were talking about unresolvable host alarms, we decided that that's enough to test hosts once, like to send the notification about resolvability of the host once a week to a user, because actually we expect that these hosts are not retired that often, so just updating the configurations once a week if it's needed is enough. Moreover, it seems to me that the reason why we are not getting the answer from the host can not only be the fact that it's retired, but that can be something else. That's why I kind of talked to my mentors that would be great if there is someone who's responsible for kind of cleaning the configuration. Then this person will get the list of this host. For example, currently it's 41 hosts that potentially must be removed from configurations. Like in order there is no access for that person to check on his own or her own whether it's really retired, to connect people who are kind of responsible for those sites and personal tests who are running on that precise site, to ask which hosts are really up to date currently and which are retired, to clean it. Yeah,
Okay.
maybe if something was not very precise in my answer, then maybe.
No, that was very precise. Thank you very much.
I can add something here, because I think we're mixing up things a little bit, because what Yana is talking about is about configuration. So we expect some results from particular set of hosts, and some hosts changed with the time because people upgrade their network, their devices, and so on. But we keep asking for these latency results for these hosts which are not there anymore. So this is what she's trying to track, like infrastructure-based alarms, not exactly if the host is alive or not.
No, totally. And what I guess what I was after was, how do you tell the difference between a change in infrastructure and the internet just being the internet and not responding? Like, right, because one failed ping doesn't necessarily mean an infrastructure change, whereas a failed ping over a week might mean an infrastructure change. Do you know what I mean?
Yeah. In this case, we know if it's one or the other by the way we query things. So what she's doing with this alarm is she's getting the configuration list of hosts and checking there for this particular host. And the other is, we have this latency data, where are the ping results that you refer to. And there we can see if we have like complete packet loss, or the host is missing, or whatever it is the case.
Okay.
So two different places to check for one or the other.
Yep, to see if they're correlated. Okay.
Yeah.
Thank you. And again, Yana, really nice talk.
Thank you very much.
Okay, any other questions for Yana? All right. Thank you all for coming. We'll have another round coming up, I think next Wednesday. Thanks again. Bye, everybody.
Bye-bye.
Take care.
Bye.
Bye.
Bye-bye.
Bye.